want to write this given polar equation. Right? So it's an equation right now relating only two variables, radius, right, and theta. We want to rewrite those equations. So, right, so with these reminding the relationships that, and for this here, I don't have to rewrite all of those other properties that we learned about polar coordinates. We almost can get, so for this property, we can almost get, see that's r, if you're looking at the r square and sine cube right here, r square and sine cube. Right? Now I'm talking about if it was r square sine square, if it was r square sine square here, which is not the case here, right? If it was sine r square sine square, then we can rewrite it as r times sine theta, and then r squared, and then the r sine theta here can be turned into an x. See what I mean? But here, unfortunately, we don't have the r. I mean, we don't have the r and the sine. We here have different powers, right? And so keep that in mind. And then the cosine right here, the cosine that we're looking at. Once again, my observation is telling me that it was cosine, but if it had the r times cosine in front, then we would turn that into an x. But right now, it only has a cosine, right? So from that observation, here's how I'm going to decide to do this for you. I'm going to divide both sides by r over r, right? Dividing both sides by r. So that means on the left-hand side here, there's an additional r. We multiply it with that r squared sine cube of theta, right? Minus 7 cosine theta. Okay, looking at that. So I just divided both sides by r right there. So the left-hand side here cancels out, right? And gives me 1. And then the right-hand side here simply 2 over. Now I'm going to, so after dividing r to both sides, and that consequently made it an additional factor in the denominator. Now I'm going to distribute that factor into each term right there. And so making it r cubed, right? Sine cube theta minus 7r times cosine theta. So now here's just like I was pointing out earlier about the observation here. We've got 2 on top. Now the r cubed, sine cubed, now they agree with the power, right? And then we can write it as r times sine theta, all cubed, okay, minus 7 times, notice that's the r times cosine theta, r times cosine theta. So now we are ready to make a substitution to bring our equation back to Cartesian equation. Okay. R equals, I have 2 over, and see, the 1 equals 2 over r times sine theta is y. So r sine theta all cubed is y cubed. Okay. And then r times cosine theta is x. So y cubed minus 7x. Right? Denominator. And so the equation right there is our final Cartesian equation. See, as long as we have arrived at an equation that has only the x and y variables, we're good to go. Now, aside from that, so let me take you to example 5 right here. We want to do the opposite way. We want to write the given Cartesian equation. So we have an equation written in Cartesian equation, but we want to write it as a polar equation. So the work is opposite. We want to go from Cartesian equation back into the polar equation. Just x squared plus y squared equals 4, for example. This equation here is a Cartesian equation. Right? It has only 2 variables. So what do we recognize here? X squared plus y squared. So x squared plus y squared in our understanding in terms of the relationships from Cartesian to polar coordinates, and r squared can equal to x squared plus y squared. Right? We can take that relationship right here. So I'm going to substitute that right into our equation. So I'm going to take that x squared plus y squared and substitute that for r squared. Now my equation becomes r squared equals 4. Saying that? Okay. And so now r squared equals 4 here. That's our polar equation. Now it has only just the polar variables, right? The r and theta variable. Of course, just have a y equals 5, for example. This equation here is a Cartesian equation. Only x and y variable. So now, you guys tell me some suggestions. What can you substitute here to bring it into the polar? Yeah. You go r sine theta equals 5. So, yes, so technically when you come right here at this point, this equation of yours is already a polar equation. But more commonly, we want to see, like in this case here, we didn't want to take the square root. I mean, we could have also taken the square, for that back to that equation, we could have taken the square root, making it plus or minus 2, right? Because taking the square root of 4, okay, we could have done that, but we tried to, but a lot of times we avoid taking square root, so we're okay with that equation there. But for an equation like this, if you can, my point now is that if you can, most commonly we're going to solve for r here. So r dividing both sides by sine of theta, we're looking at 5 over sine of theta. This form right here is the more preferred one, even though that was already your correct answer right here. But here we are expressing r as a function of theta, like what I explained in the earlier part of the lecture. Okay. So just like that, right? So you can easily see that in another problem. You can say x equals 3, for example. Right? This equation here, sorry now, it's a vertical line, right? Graphically speaking, it's a vertical line. 1, 2, 3 on the x-axis, right? X equals 3 is this line right here. So you put any point on there. Make some distance r with angle theta. So you put a point here, it has some other angle theta with this distance r, right? That's why we can rewrite this equation. We can rewrite any point on this line right here, right? In terms of the polar equation. So here again, see, x here can be substituted by r, but this time cosine theta, right? Equals 3. You guys agree there? Okay, so anywhere you see the x variable, the x Cartesian variable, okay, you can substitute that with r cosine theta. And then from there, so now, yes, this is already your polar equation. But if you want, more commonly, it's preferred as a function of theta. So we're going to move to the next step, divide both sides by cosine of theta. Okay. So now we're looking at r equals 3 over cosine of theta. This is a better form of that. And these are the easy one that's still building your fundamentals right here. So now, look at y equals 5x squared, for example. So 5x squared is a Cartesian equation. The graph here is a nice parabolic shape, right? I'm lying a little bit about the shape. It should be a lot more narrow. Be a very narrow graph here. But again, any point on that, right? Make some radius and some angle theta. See what I'm saying? Right? So in that case here, well, we have done that before. R, I mean, y can be substituted by r times sine theta. Good? And then that equals to 5, and then x here can be substituted by, in parentheses, because there's a square, right? So r cosine theta. Good. Right? And then we put the square, so the square now is going to distribute. So left hand side is r sine theta. The right hand side is 5 times r squared cosine squared theta. Right? And then, so that's already the polar equation, but then we want to divide both sides here by r times cosine squared theta. R times cosine squared theta. We want to solve for r. I should have done also, I should have divided by 5 r cosine squared. Okay. Now the right hand side becomes r. Because the cosine squared got cancelled, right? The r here got cancelled with the r squared, leaving me just an r. The 5 got cancelled out, right? And then the left hand side here gives me sine theta over 5 cosine squared of theta. So we have solved for r as a function of theta. We want to stop at this better form of that, even though they're all polar equations. Okay. And so now that's how we're converting between the equations in different forms, right? Cartesian form or polar form here. The more challenging part is to be able to graph a polar equation. So I'm going to do one demonstration example over here. So let's look at example. And so any one of these is I'm gonna call that example 6 here. It's one problem, and it's good enough for you guys to get a good hang of that. And then I'm gonna introduce some technology that can assist your working. So let's say you want to graph, right? You want to graph R equals cosine theta. What we have here is a polar equation. So before we get into the actual graphing, now, like I said earlier, the point now is that R is written as a some function of theta, in the way how it looks like that. And then your theta right here is the independent, right? Independent variable. And then your R right here is the dependent variable. Everyone here should be familiar with those terms, right? The dependent and independent variable. Independent variable means you can independently choose values. And then the dependent one means the R comes out based on whatever is determined by the cosine of theta that we have independently chosen. Okay. And so, once we're looking at that nature again, that R is the dependent variable and theta is the independent variable. The first, in order to draw a graph of this polar curve again, of this polar equation, we're gonna construct table of values. Okay? Theta is the independent variable. We're gonna say one column for that, or being calculated by doing cosine of theta. So we're gonna have to construct a T table or the table of values. There are so many ways you can understand that, right? So once again, hold out have your unit circle ready, and then it may go a little lengthy here before we can get to see some pictures, some good pictures of that. So I may need to extend that table. Okay. And this is also a good learning check for everyone here. Okay. So let's just start out on the unit circle. When theta equals 0, what's your cosine of theta? 1. So that means the radius in this case equals 1. Right? So now the 1 right here is the radius. Are we good there? And then at the same time, go ahead, put that point on your plot again. See, this is one pair of polar points right here. Radius 1, angle 0. Radius 1. It's a little backward when we build a table here, but it's radius 1, right? Angle 0. So when you put that point, you can define your scale. This is 1 here, so angle 0, right? Radius 1. Sounds good there? So we put the point right here. You guys agree? Right. So right here I have that point. Radius 1, angle 0. Right? You guys here, let me move that a little bit. Like that. Radius 1, right? Angle 0. That's our angle. That's our point. Agreed? Right? And now I'm going to keep swinging back and forth between that between the graph here and the board. So let's go on to the next one. The next common one on your unit circle is a pi over 6, right? Which is a 30 degrees. Pi over 6 or 30 degrees, right? Either way you want to see it. See what I mean? So, cosine value of that. Okay, root 3 over 2, right? So 30 degrees is about here. So I'm saying that root 3 over 2 is a little bit shorter, right? Like that. Here. Right? Now write on my table of values. 5, 6. That's root 3 over 2, so it puts us right about there. Everybody with me still? So we have, the idea is we increase the angle. You guys can all see it, right? I hope I'm not blocking the screen or anything like that, but as the angle opens up, right? The angle opens up positive. The radius gets changed, right? The radius changed. So at first it was starting out radius 1, but now it gets shorter, right? But I mean, does it always get shorter? We'll find out, right? As we go through the table values. But that point right here is, see, 30 degrees, right? So the pi over, I mean, that's the coordinates, but the software I'm using here doesn't show the actual polar coordinates. It's supposedly pi over 6 for the angle and root 3 over 2 for that. It doesn't even show root form for the technology we're using here. I'm using here. And then the next one is a pi over 4, right? Going up, which is the 45 degrees. So cosine value of that, 2 over 2, yes. And then so on your graph here, it pops out a point just right about here. Let me put that in, pi over 4. See that new point that just popped in? It's that point right there, right? And so that length from the pole out to that's exactly on which decimal you get, right? That's exactly what the software square root 2 over 2, that length again. And so for us right here, of course, we can't really draw it that perfectly anymore, but basically it's shorter than that distance from root 3 over 2, right? You guys with me on that? Okay, and so let's continue. The next one here is pi over 3, which is 60 degrees angle. Right? 1/2. And this one here is okay for us to put it on the graph. So right at 45 degrees on this graph, here we're about there, right? That's 45 degrees, and now 60 degrees, we're about here. See what I mean? There were ways for us to do that manually as well, but I just want to use software here to do that. Right, pi over 3, 1/2. So the idea now, and so you can see that as the angle opens up, right, you got different radius right there. 0, pi over 6, pi over 4, right, pi over 3. The radius gets shorter and shorter, right? Does it seem to form some kind of shape yet? Well, if we don't see that, we can keep going. So the next one is next known one on the unit circle is pi over 2, which is a 90 degrees angle. Cosine of 90 degrees angle, 0. So radius 0. So that means when we hit to exactly, think about on this sketch version, when we hit exactly that 90 degree angle, the radius shrinks to 0. You see what I mean? Right. So far it looks like I'm forming into a shape like this. Guys, observe what I'm doing here. It goes into a shape like this. See? Like a half circle. Because of course we didn't draw those angles in between, but as we keep steadily changing, right, and forming to a shape, all of these points forming to a path that goes a semicircle up, right, and hits back to that point right here. See what I mean? Right. And so now let me show that on the screen. Okay. On the screen now, I'm going to look at pi over 2. See, the new point just now popped out right here at 0. Right. So these points right here now they really seem to be forming into a nice on the picture right here, right? With much better precision. Yes, it does form into something specifically semicircle above the x-axis. Okay. And then we can just continue. And so let me point out a few other points for you guys. So now I'm going to go to larger than 90 degrees, right? We're going to go to 2 pi over 3. Right? You guys go ahead and calculate that for me. And then you got 3 pi over 4. Right? And then you got 5 pi over 6. Right? And then you're going to have a pi again. Right? So let's go up to that particular point again. See what I mean? Go ahead and get those cosine values first. Right? So that one here is negative 1/2, right? Radius negative. See what I'm saying? So the way how you read this pair. See, for this pair right here specifically, and we've learned all of this, right? That means what? Negative 1/2 of radius, negative radius, right? Angle 2 pi over 3. See what I mean? Right? So on your sketch, think about it. Right? On your sketch, right? You want to open the angle to 2 pi over 3. See, the 2 pi over 3 angle is right about here. But in that opening up angle, the negative radius has to be some point on this side, right? See what I'm saying? So the magnitude of the radius is always 1/2, but it's on the opposite side. Instead of aligning with the direction of your angle. Okay? See what I mean? Right? So now I'm going to really put in the points. Okay, so now, that point right here, let's look at 2 pi over 3 here. You see how that new point just popped out? That new point just popped out again. See, just like what I was describing. Okay? So at 2 pi over 3, this angle over here, right? We have a point that popped out right there. See what I mean? Right? Now back on the board. Okay. So now these other values, negative root 2 over 2. 3 over 2. Then so what's your? Anyone got the last one here for pi? Negative 1. Okay. So all of these things again, it's going to happen. It happens right there on the graph. Okay, so you turn over. And again, you see negative radius all over in this case here. So the pi over 4. Over 4, so 3 pi over 4. The negative root 2 over 2 is about this value right there. So just now, you see, just now at that angle, pi over 4, 3 pi over 4 is right here, right? And we're looking at the negative radius. That has to be down below. That's the way I'm seeing it, right? And so the shape is kind of like a loop around shape there by far. And then I'm going to complete with the next point right here. So there's a 5 or 6, right? So the angle is right about here, but I'm expecting some other point that's standing on this side here of my graph. That's the angle. I'm expecting some point about there, where my mouse cursor is at, about there. Right? So, right? And that's just exactly where that point is. Good. All right. And then the last one here, I'm going to put right there at pi. Okay. So pi gives me a negative 1, which is falling exactly with that point right there. Okay. So we have now completed one circle. Okay. So the pi over 6 angle, right? Angle opening up from the positive x-axis, opening up to 5 or 6, right? But it gives a negative radius. So when it opens up exactly 180 degrees, right? Over here. So 1 is here, but negative 1 is going to be on the other side, right? Relative to that angle itself. Okay. So we got the graph, but so in the end, really, let me show you guys this technology right here. So I will share this link. Right, this graphing tool with Desmos here on your Canvas account, so that you can have it. You can put in the table of values just like how I've been doing. Right? And then in case that you're not sure what to do, you can always view the video recording here because I also have the on-screen clip. You guys can view it so that you can learn how to use it. Now, but when later on we don't always have time to sit down and draw the table. Right? We don't always have time. The table is the building block right here, but what's the point of having technology? There's no way we have time to always go through a table. So I'm going to share with you guys a technology that you can use that for getting a good graph here. So you see this tool right here I developed for my students to use here. So you just type in, see the R of theta, the function in terms of theta we do it here is the cosine of theta, right? It's type COS, right? And in parentheses it's type THE. TA right there, that's for short. That's how Desmos will understand theta. So, I mean, and you gotta use it when you decide to use this technology. You have to use theta for the polar coordinates. Okay, so you go with that, and then you see by default when this program is delivered to you, right? You're gonna see that these things right here are actually unchecked. So you gotta make sure you check with that, and then you check with that, and then the polar curve will appear out. So now here's how I'm doing it. So I should have used degrees right here, but the N right here means the number of degrees. So right now you're at 0 degrees, just like on the table that we've had, right? So now I'm going to drag out right here. I'm going to drag to increase the rotation counterclockwise. Right? So now in the meanwhile, you observe right then, as I drag it up, right, as the angle start opening up right here, I start having some radius. So first radius, and maybe let me put that even closer zoom right here. Right? So let's go back to 0 angle. Right. I'm going to put it in a really close zoom right here. All right, radius 1. So I'm going to drag up. Right. Do you see the change now? Okay. So it was radius 1, right? And then it starts getting shorter. You observe that. And then I'm going to keep dragging the handle further, right? And on my handle, you can see that there's a solid side right here. The solid side is the positive side of the radius, and then anytime that our point sinks to the negative side right here, it's gonna appear on the dotted side right here of our handle. Okay, so now I'm gonna keep increasing. So right now I'm at 34. So think about right at 30 that we were at that angle pi over 6 again. See, it's consistent. It's consistent with our click that without floating point earlier. Right? So when you guys receive this thing, have fun with dragging it out, right? So when we move to pi over 2, which is the 90 degrees angle, we have completed the exact half circle again. See that? Right? And then on our table, we went only to pi, which is n equals, which is in degrees 180. So I'm going to keep going until my number. See, when it comes to here, the positive side of the radius is on the solid side, and then the points now is going to be, when we go past pi over 2, the point is going to stay on the negative side of the radius again, right? And that's why now you can read the point and the behavior of the point. Let me move it here. It's easier for everyone to deal with that, right? And then that now is going to go just like that. When we are exactly at 180, right? When we are exactly at 180, we land right there, which completes the circle. But then what if we go even further? What if we go even further? Then you can see that with the demonstration here, I didn't want to take too much time of yours with the table of values, but we can technically keep going further, right? So now we're going past 180. You see that it's still on the negative side, right? Because the angles are down here. The actual angles are down here. Right? But then the point, the plotted point, the polar points are actually on the negative side. So that's why it's repeating that circle loop right there. And then we're going to keep increasing that, right? And it's on the, right? That's how it's happening. Now it's swinging back to the positive side of the angle, right? And then it completes one rotation, 360. You know what I mean? Right? And then if you want to go with more rotation, sometimes you may need to go more rotation, right? You can click right on that thing right here, and then you change your up limit right here to some number. Right now I got it defaulted to 720, which is 2 rotations right here. But you can also go to whatever that you want. Okay? All right. So that's how we see the graph of this function. In this example, that's just the fundamental building block. We got to go through the table of values, and then once you understand what's going on right here, I'll just let you guys use technology for that. Okay? I mean, your TI calculator also has a feature, but when you use your TI calculator, it just, once you finish typing it in, it just, hey, here you go, here's the picture.
All right, so now on a TI calculator, this is how we can get the graph of a polar equation. So first, with your TI calculator, we need to adjust a couple of settings right here before we can get the graph. So we go to mode, and right now on my current calculator, it's indicating as function mode. So we scroll down to that and change that over to polar coordinates. And left and right arrow is to change to different functions. Hit enter, and we need to keep our calculators in radians. And so it's the calculator that I use right now is currently in radians. Hit enter one more time to make sure, and we can get out of the settings. And so now we are ready for getting the graph of a polar equation. We go to y equals button right here, and now we can just simply pick one line and start typing in our graph. So the function that I used in the example is a cosine. So we go cosine. Theta is found in this key right here. This is the variable key. So now in polar mode, it's going to automatically pop out theta. So we have cosine of theta. I'm going to hit enter to get out of that line, and we click on graph, and this is our polar graph. And just as I said, it's simply just going to show the graph without seeing how the graph moves depending on the change of the angle theta. But now with this given graph right here, we can click on zoom. You can go zoom in to have a closer view. Now I'm going to change that cursor to somewhere in the middle of the loop. Hit enter, and now it's going to zoom in once. We can hit enter again to zoom in a little further. And now with the default zoom setting of the calculator here, then the scaling here is going to be a little bit off scale compared to what we're normally seeing. So if you want to see like the usual scaling right here, one ratio 1 by 1, then we go to zoom, click on zoom square. And now with this zoom scaling right here, then it's on the ratio 1:1 on the x-axis and on the y-axis. And now that puts us in the square zoom right here.